Okay, so I'm here today to talk about automated solution of heterogeneous agent models, and in the spirit of Denny's introduction, I'm going to include some sort of general material on both heterogeneous agent models and on macro models in general and how these are related before I get into some of the specifics about the class that I work with.
Yeah, it's kind of doing.
Let's use the keyboard. Okay, the keyboard's not the thing for this either.
The big button is fell over.
The big button doesn't do it. None of the buttons is doing
Maybe
it
click
actually.
it once.
Yeah.
Yeah. Okay. Click.
Again, now we get the worst.
Okay. The clicker is now working. Great. So traditional macro models, what we're interested in is aggregate behavior of the economy. So that's sort of what makes it macro. So we're thinking about time series of things like aggregate income, which we call GDP, or inflation rates, which is an aggregate of all the price changes. And what heterogeneous agent macroeconomics tries to do is incorporate information on the distributions of the components that add up to these aggregates. So inequality of income, wealth, or distribution of prices across firms. We now have data on this across various types of agents. And probably the most popular class, increasingly popular actually, of macroeconomic models of these aggregates is what's known as a dynamic stochastic general equilibrium model. So what that means is dynamic stochastic, we want a probability model of these time series, and general equilibrium means that we want a causal model of the relationships between them, so that we can do policy, describe counterfactuals, and describe sort of how individuals will react to our policies. So I'm going to introduce sort of general class of equations for heterogeneous agent models, and then I'll tell you some things about DSGE solution algorithms, and then say some things about how these can be extended relatively straightforwardly to heterogeneous agent models, and maybe get through just a numerical example. So the way to think about what a heterogeneous agent model is it's built up of a set of blocks that is very similar to some in this community might know what a mean field game is. So we're interested in that kind of mean field behavior, but really what we want is the stochastic aggregates out of it. That's the most important part. And so we add some shocks to that. So typically speaking, the first block is what the individual agents do. And they're optimizing some intertemporal decision problem with respect to some idiosyncratic states. So I call them X here. And they're making some choices Y based on those idiosyncratic states. They're facing some shocks. Idiosyncratic shocks, so we can think like each individual person has their income, their wages go up and down stochastically based on the state of the economy, and they want to decide their consumption and savings. And we set up a Bellman equation for that with some dynamics. And the important part of this that makes this macro is that some aggregate features of the economy enter into this. And what makes it mean field is that they're taken as given. So I denote this P here. Typically, these are things like prices or interest rates, and they take the dynamics as given. What makes it general equilibrium is that those dynamics have to be consistent with the behavior of all the individual agents. And so in particular, the distribution of idiosyncratic states, Fx, is determined by the decision rules of each of the individual agents. So the optimizing behavior that we call G enters in and induces a Kolmogorov forward equation for what, say, the wealth distribution will look like tomorrow, given the wealth distribution today. And so there's this adding up constraint. And then there's some equations that determine the aggregate variables. There's some exogenous part. We can think about this as shock to the economy. There's some sort of pandemic or monetary policy makers move interest rates for random reasons. And then there's some endogenous part, which is determined by the behavior of the individual agents, but just through the distributions. And so we can think about this as like supply and demand equations. So people okay with the setup? Great. And so what is our solution concept for some of these models? And it turns out that this is the solution concept also for classic aggregate dynamic stochastic general equilibrium models. What we do is we just group all of these equations into a system of expectational difference equations there. So those expectations are the expectations induced by the equilibrium of the model. And there's some state variable X that determines what the economy is doing right now, some jump or control variable Y that's determined by it. And then there's some recursive dynamics. The prime indicates what the variables are going to be tomorrow. And a solution is a system of functions that determines the control given the state and a log motion for the state. So for each individual, these would be the same as the individual problem, but really we should think about these as for the aggregate economy as well. And we want these functions to be consistent with all the equilibrium conditions, which is just to say that if we plug them in, then the optimality conditions hold, the equilibrium conditions hold. And typically there's one thing that we often don't write in the equations, but that is a constraint, which is something like a terminal condition. Usually we write infinite period problems, so there's no terminal period. So you have something known as a transversality condition. Madi's talk will be all about this, but the way we can think about this is the dynamics are determined by all of these equations right here. And then to ensure a stable solution, you have to make sure that the control variable on the y-axis jumps up to the point that is going to converge to the equilibrium. And so that is one of the complications of the computation that we'll talk about. So typical DSGE solution algorithms, there's a couple of classes. When I say projection, this is a different type of projection. Here we're projecting those functions onto a basis. So we're representing this H or G function by some tractable function class like splines or neural networks. And then we're finding H and G in the class that approximately satisfy those equilibrium conditions, for example, by minimizing a measure misfit or solving a variational inequality. And you can do that with something like gradient descent or many other methods. Probably much more standard in the sense that it's the default in Dynair, which the European Central Bank, this is their sort of generic macro software that every macroeconomist has at least some experience with. You just type up your model and it does a solution and people don't think about it. This is doing what's known as a perturbation approach, which gives you a local solution, which is very fast, taking a Taylor expansion of your equilibrium conditions around a steady state in which you shut off all the shocks. And so this induces a system of matrix equations, which give you the Taylor expansion for your policy functions, H and G. And among the benefits, aside from speed of linearity from this, is that it's easy to impose this terminal condition by imposing a condition on the spectral radius of this dynamics function, if that spectral radius is less than 1, in the negative half of the complex plane for the continuous time version. Then this works, and it turns out that you can impose conditions on the primitives. These are often referred to as the Blanchard-Kim conditions, which ensure that this holds. So this is an additional constraint, and it's determined by a generalized eigenvalue problem that gets solved and is the main sort of computational cost for this class of algorithms. So let me introduce that formally. We start with our equilibrium conditions. Showed you. You find a steady state by some nonlinear equation solver. So the steady state is just values of the equilibrium that are unchanging, so they're not functions. This is low dimensional. use any solver you want. Take your Taylor expansion with respect to X, and notice that this induces a quadratic matrix equation because of the recursive nature of the solution that's required. And so in order to solve that, what you want to do is take these Jacobians, those induce a set of matrices that I'll call B and A, and then to get these generalized eigenvalues, which are solutions of lambda A minus B inverse is unbounded, you apply the QZ algorithm, which gives you the sorted eigenvalues along a set of block triangular operators. And in particular, because they're sorted, you can just figure which are the ones inside the unit circle and which are the ones outside. And you can define the system just in terms of the upper and lower triangular blocks of this. And so the Blanchard-Kahn condition just says the lower block of this U matrix is invertible. That's actually a substantive condition in many member models. There's quite a large literature on this. It requires that you have a policy that jumps up to stabilize any unstable components of the process. So if you have some behavioral agents and some rational agents in your model, you need to make sure that there's enough free variables to ensure stability. And there's closed form formulas that are easy to implement, but I'm probably short for time. So how do we do this with heterogeneous agents? So high dimensional models are generally hard to solve, but I don't know that this is actually what Jeffrey Hinton says, but this is sort of the trick that everybody uses to deal with 14-dimensional space. Close your eyes, visualize a 3-dimensional space, and say 14 to yourself very loudly. And so heterogeneous agent models, these are really functional equations. We're interested in solving for maps that take as inputs these distributions and output new distributions. So these are not 14, but infinite dimensional. So what I'm going to introduce is a much more powerful version of this trick. For an infinite dimensional space, close your eyes and say the word Hilbert while visualizing a 3-dimensional space. And that's it. So formally, the reason that this works is that you can show that if you write the equations for the perturbation solution, at least the way that I wrote them, if the states are functions or distributions in Hilbert space, these have been written in a coordinate or dimension-free form. And so long as you're including this distribution, state distribution as policy function in your state space, you can replace the Jacobians with functional derivatives. You can replace the eigenvalues with spectra of operators, and exactly the same formulas apply. There's some existence and uniqueness conditions that are sort of analogous to these Blanchard-Kahn conditions. We still have some computational problems here. This is sort of nice for sort of characterizing what a solution looks like. But we need to actually compute these functional derivatives, and we need to solve the generalized eigen vector problem in infinite dimensional spaces. And so what we're going to do is we're going to go back to finite dimensional spaces, give ourselves coordinates. This is an approach popularized by Ryder and sort of ubiquitous at this point. You take your function, Parseval's identity says it's equal in Hilbert space to an infinite sum of basis vectors with some coefficients, and you just cut off at k basis vectors. And then you use the coefficients of the basis vectors as your state variables. And so the Jacobians now are Euclidean derivatives, and you have a finite dimensional matrix. And so how do you compute the generalized eigenvalues of a finite dimensional pair of matrices? Well, you just use standard linear algebra solvers.
Is this technically a reproducing kernel Hilbert space? Like,
it is very specifically not a reproducing kernel Hilbert space. So I could get this to work in L2. Generally speaking, the representer property doesn't have to hold. You can use RKHS methods for other components, but generally speaking, you can't generally ensure that the equilibrium lives in an RKHS in these models. That's a minor detail, but effectively L2.
how do you guarantee the representation basis? Like, it's just like the particular policy space has to satisfy that representation issue, or?
I have a set of sufficient conditions on the model. Thank you for setting this up for me. I have a set of sufficient conditions on the model which ensure that that basis representation is a good representation. And so basically we need to make sure that these finite approximations are reasonable even for equilibrium functions, which could be sort of anything that's determined by these stochastic shocks. So we can't just say, here's a function, we just assume it's in this space because the space is determined by equilibria. But if you build your function in the right way, you can ensure that it is. And a simple way to do this is to build it out of blocks that have simple properties. So in particular, if it's built out of linear integral operators, so multiply your function by a kernel function and then integrate, or pointwise nonlinear compositions. So you take your function and compose it with another function. Then your system of equations looks a lot like a neural network. You have pointwise nonlinearities and linear maps. And it turns out that you can get your system of equations to look like this, possibly after a change of variables trick. So you add noise, you move the evaluation inside the density. One way of thinking what you're doing here for the ML people in the audience is that your Kolmogorov forward equation in this case becomes a normalizing flow, which allows you to have a well-defined and smooth density, which is amenable to approximation using standard function approximation. And so the solution algorithm, I'll give you the on the grid version. This is equivalent to projecting onto a histogram basis. Is you replace the function by its values at set grid points. You replace the integral operators by just sums, possibly with some quadrature weights. And then now you have a discrete model in terms of this discrete set of states. And so you solve for the steady state by a nonlinear solver. You linearize by standard autodiff or symbolic differentiation routines, and then you apply the standard RE solution algorithms. In the case where you're projecting onto other bases, there's some additional transformations that need to be done to basically interpolate those grid points. There's some modifications on that. So what kind of guarantees can you get for this result? You can show under all of those conditions that the Fauché derivatives converge in what's known as operator norm, which is to say uniformly over all inputs in L2. And the rates will depend on the smoothness and structure and choice of basis functions. If everything is Lipschitz, so recall we're cutting off at K, roughly order K to the -1/2D if there's sort of the idiosyncratic states are d-dimensional. And then once you have these derivatives converging, then the solutions will also converge in the same. So that's an optimal rate because you could just say, here's already my, you just write out the solution mapping and don't do any solving. And then you'd still have to get these same rates to a constant. So not going to go through a full proof here, but basically the reason that works is that if your model looks like a neural network, then its derivatives look like a free-form equation. So they look like this integral operator. And you can calculate the basis approximation of this integral operator, and you can show using an inequality known as Young's inequality that the operator norm is dominated by the L infinity norm, and so you can just use function approx 5. Okay, yeah, 5 is easy. -2. Oh, sorry. Yeah, okay. Then I will act, okay, and then that gives you with a perturbation inequality for QC. So convergence. Yeah.
I'm just curious about this like truncation error in terms of K. Like how is this, like initially you set up this like Kolmogorov forward equation for this problem, and you need to like estimate some underlying distribution, some amount of accuracy, and like is K related to like how good your estimate is, like,
So the
Where-
trick
where
here
are
is
these
that there's no estimation whatsoever. This is, you're given a fixed problem and we're just numerically saying, if this were the system of equations, if there's estimation, then you also introduce statistical error.
okay, so like you have oracle access to true gradient evaluations.
Yeah, exactly.
But in reality too,
You can plug in noisy estimates and you can sort of get them in.
you would need to get some epsilon deltas there, got it.
Let's just say we have some consumption savings examples you can show, just rather than go through the equations, you get some functions, you get the steady state, and you can show what the perturbations of the functions look like in response to shocks. So let me conclude. The methods that I just described to you are extremely widespread. Basically, every central bank now, all the models that they're using are what's known as Hank models, which are versions that are this with some monetary policy block in the model. But there's a lot of work to do in terms of getting the empirics right and incorporating nonlinear. So other people will talk about today. So sorry for going on.
Can you just give us a takeaway from your pictures at the end? Like, what were you comparing to? Are you comparing to what's the dynaire or whatever the standard?
So this is just a numerical example of applying the algorithm.
Like, how
So
did
I
you-
do have convergent. So I have some other examples where I have like measuring the convergence error as a function of k relative to some known solution. Dynaire, really all that is, that's the version of this algorithm that solves the RE.
Sorry, it doesn't have to be dynaire. I just meant, is there some kind of baseline? Is there some way we should be judging the, how good is this?
Yeah, so typically, there are a variety of measures in terms of basically like equilibrium error that people use. And this is, so because it's a local approach, basically it requires the shocks to be relatively small to be a good approximation. And the answer for that is, can be terrible for certain class of models because you're Taylor spending a function that may be arbitrarily nonlinear. But for a lot of the models that people use in central banks, this is sort of measures of things like Euler equation error, which is the L2 error, the Euler equation are modest, I would say. And mostly that's coming from the Taylor expansion part, not from the truncation. You can truncate the